I want to kick off our deep dive today with the fact that it really recontextualizes everything you look at. Light itself has no color at all.
That is a profound idea, isn't it? Because we live in a world that feels defined by color.
Completely.
But you're absolutely right. The color we perceive is purely a function of an interaction between that light and, well, matter.
So it's about what the light hits.
Exactly. Whether it's the atoms in a piece of glass, the, microscopic structures on a butterfly's wing, or ultimately the biological sensors in our own eyes.
And that's our mission for this deep dive. We're going to explore the source material to reveal how physics literally constructs our visual world.
Yeah.
We'll go from the fundamental nature of light, that whole particle versus wave debate,
Right.
all the way up to really advanced color technologies, things like lasers, and even electronic paper.
And we have to start at that foundation, which historically was this huge conflict. For, hundreds of years, physicists argued about it. Is light made of tiny, discrete particles, corpuscles, they called them, or is it a continuous wave like a ripple in a pond?
And the sources point out that each theory demanded a very specific, testable outcome.
It did. If light was a wave, the theory said that when it enters a denser medium, say water from air, it has to slow down. And that slowing down is what causes it to bend, what we call refraction.
But the particle theory said the opposite.
The complete opposite. The corpuscle theory suggested that forces pulling the particle into the water should actually make it speed up.
And for decades, it was just too fast to measure.
It was almost impossible, yeah. But eventually the technology caught up, and the wave theory's prediction was confirmed. Light does move more slowly in water.
So, case closed. Light's a wave.
That's what it seemed like until, the 20th century came along and complicated everything, as physics tends to do.
Of course.
The modern view we use today is, well, it's elegant, but maybe a little confusing. When you look at light interacting with matter at the atomic scale, like one photon hitting one electron, it's best described as a particle, a photon.
Like a tiny billiard ball with a specific amount of energy.
That's a great analogy. It delivers a specific punch. But when you look at a huge flood of light, millions and millions of photons all moving together.
The math suddenly wants you to treat it like a wave.
Perfectly put. The statistical behavior of a large number of photons is represented perfectly by an electromagnetic wave. So, both are true. Photons are the packets of energy, and the wave is the mathematical description of the whole beam.
So once that light, that wave of photons hits us, the physics kind of hands off to biology.
It does.
We split the visible spectrum, red to violet. But as we said, that's totally artificial. It's just a continuous gradient of wavelengths.
And what's fascinating is that the entire human experience of color relies on just 3 types of sensors in our eyes. 3 types of cone cells: L, M, and S.
L for long, M for medium, S for short.
Exactly. The L cones are most sensitive to longer wavelengths, peaking around 560 nanometers, which we see as red. M cones get the middle, peaking around 530 nanometers, so green. And the S cones handle the short wavelengths, peaking near 420 nanometers, which is blue.
It's amazing. 3 sensors. But our brain processes that into millions of distinct colors.
It's all in the processing. And if you look at the data on human vision, you'll find something really telling. We're not equally sensitive across that whole spectrum.
Oh, that's interesting.
We are optimally sensitive overall to green light. The peak is right around 555 nanometers in that green-yellow part of the spectrum.
So we are literally tuned for green. Is that why camouflage often involves greens and browns? Or why high visibility safety vests are that bright lime yellow color?
That's absolute part of it. Our vision is optimized for the environment where we evolved, which was, full of plants. Green is the information-dense part of our world.
Which brings us to how we engineer color. There are 2 main methods. Let's start with additive color, which is all about mixing beams of light.
Right. Additive color is what makes your television or your phone screen work. It's based on the 3 additive primary colors: red, green, and blue. RGB.
So the screen is just a grid of tiny red, green, and blue lights.
Essentially, yes. Tiny dots of phosphors. And the crucial thing is, when you mix equal amounts of these 3 lights, you get white light.
Then there's the other way, subtractive coloration. This is paint, dyes, ink.
And it works in the completely opposite way. It works by depletion. When white light, which contains all the colors, hits a blue pigment, that pigment is actually absorbing the red and green parts of the light.
And it leaves the blue to bounce back to our eye.
It depletes the white light, leaving only the blue for you to see. So the subtractive primaries, cyan, magenta, and yellow, are the exact complements to the additive ones.
So if cyan is a primary, what does it subtract or absorbed?
Cyan is basically minus red. It absorbs red light. Magenta absorbs green, and yellow absorbs blue. If you overlap all three, they should, in theory, absorb all light and give you black.
But they don't, which is why my printer is always asking for a black ink cartridge.
Exactly right. In the real world, when you mix CMY pigments, you usually get a sort of muddy brown, not a true deep black. It's a physical limitation. So in printing, we add a dedicated black component. That's the K for key or black in the CMYK
So
system.
you get those really deep, dark tones.
For deep tones and sharp text, yeah.
Okay, let's move beyond pigments and talk about how the actual physical structure of materials can create color, structural color. The sources say all the big interactions, reflection, refraction, scattering, they're all wavelength dependent and can produce color.
They can. Let's take refraction, the bending of light. It's all defined by a material's refractive index, which is just a measure of how much it slows light down. A higher index means more bending.
And this is where we get those incredible aha moments, like how some animals in nature have achieved near invisibility.
It's a fantastic example of natural engineering. A lot of marine animals, like jellyfish, are almost invisible because their internal body fluids have a refractive index that's almost perfectly matched the seawater around them.
So the light just doesn't know it's crossed a boundary.
It passes straight from the water into the animal without slowing down, without bending, without reflecting. The surface basically vanishes, making the animal incredibly hard to see.
So if you put a piece of glass in a liquid with the same refractive index,
It would effectively disappear. Yes, you wouldn't see the boundary. We actually use this idea in something called GR optics graded refractive index, where the index changes gradually to eliminate reflection. Moth eyes do this naturally.
speaking of reflection, what about those vibrant, shimmering colors you see in a soap bubble or an oil slick, that iridescence?
That's thin film interference, and it's all about geometry. When light hits a very thin, transparent film, some of it reflects off the front surface,
Okay.
but some of it enters the film, travels through it, reflects off the back surface, and then comes out. That second wave of light has traveled a slightly longer path.
And because that path difference is tiny, on the order of nanometers, it gets the light waves out of sync with each other.
Precisely. When the two reflected waves recombine, if they're perfectly in sync, they add up constructive interference, and you see a bright color. If they're perfectly out of sync, they cancel each other out destructive interference, and that color disappears.
And since that path difference depends on the wavelength, different colors are enhanced at different thicknesses.
That's it. As the soap bubble gets thinner, the thickness changes, and the color you see shifts.
And we use this to prevent reflection on camera lenses, right?
We do. Anti-reflection coatings, or AR layers, are just very precisely engineered thin films, often magnesium fluoride. The thickness is calculated to cause destructive interference right in the middle of the visible spectrum, around 550 nanometers.
Which cuts down on glare.
Hugely. It maximizes the light that actually goes through the lens.
So let's scale up from nanometers to, say, miles of atmosphere. Is the blue color of the sky also a form of structural color?
It is, but through a different interaction. Scattering, specifically Rayleigh scattering. This happens when light interacts with particles much smaller than its wavelength, like the nitrogen and oxygen molecules in the air.
And the key physics here, as the sources note, is that the amount of scattering is proportional to the inverse fourth power of the wavelength.
It is. Let's unpack that, because that fourth power is everything.
It sounds extreme.
It is. It means shorter wavelengths get scattered immensely more strongly. Blue light has about half the wavelength of red light. So if you do the math, that means blue light is scattered roughly 16 times more effectively than red light.
16 times.
Wow. So as sunlight comes into the atmosphere, the blue light is just scattered everywhere in all directions, making the whole sky appear blue to us.
Which also explains a red sunset.
It does. At sunset, the light is traveling through a much thicker slice of the atmosphere to get to your eye. Over that long distance, almost all of the blue light has been scattered away.
So only the red and orange wavelengths make it through.
Exactly. They are the ones that survive the long journey, and they tint the sun and the clouds those spectacular colors. We see this in nature, too. The brilliant blue of some butterfly wings, like the Papilios almosus, isn't pigment. It's light scattering off microscopic air-filled layers in their scales.
Now let's shift gears. We need to move into the realm where energy exchange dictates color. And for that, we have to really embrace the photon concept, where energy is tied directly to frequency.
Right. This is where we go from color from geometry to color from energy. When you look at isolated atoms or ions, they don't emit a continuous spectrum. They emit light at very sharp, discrete wavelengths, a line spectrum.
And that happens when an electron drops from a higher energy level to a lower one.
And the precise energy difference between those two levels, delta E, dictates the exact frequency, the exact color of the photon that's emitted.
And that ability to control and isolate a single frequency, that's the core principle behind a laser.
It is. LASER is an acronym. It stands for Light Amplification by Stimulated Emission of Radiation. The breakthrough was figuring out how to stimulate that emission.
Instead of just waiting for it to happen on its own.
Exactly. Normally, an excited atom just spontaneously spits out a photon in a random direction at a random time. But in stimulated emission, you hit an already excited atom with an incoming photon. That triggers the atom to release a second photon that is a perfect clone of the first one.
A clone.
Identical. Same frequency, same phase, same polarization. They're perfectly coherent. And that coherence is what gives laser light its power. That incredibly focused, pure-colored beam.
We also use this kind of energy exchange to create cold light, or luminescence, which is in a lot of our lighting systems.
Luminescence is just light emission that doesn't come from heat, like a fire. And we usually split it into two types, based on how fast the light comes out. Fluorescence is basically immediate.
It's fast because the electron transition is easy, physically speaking.
It's what's called spin-allowed, a direct, easy path. Then you have phosphorescence, which is the delayed release. Think glow-in-the-dark stickers.
Right.
In that case, the electron has to take a longer, more complicated path home, a spin-forbidden transition. It's like a detour, so the energy release can be delayed for seconds, minutes, even hours.
And how is that applied in something like a standard fluorescent lamp?
In those tubes, a high voltage zaps mercury atoms, which then emit high energy but invisible ultraviolet radiation, UV light.
Okay.
That UV light then hits a phosphor coating on the inside of the glass tube. And that phosphor coating is the key. It absorbs the high-energy UV and re-emits it as lower-energy visible light.
And you could mix the phosphors to get different shades of white.
You can. Modern lamps are often trichromatic. They mix 3 phosphors designed to emphasize red, green, and blue, which gives you a much more balanced, natural-looking white light.
And we can even apply these ideas to things that look like old-fashioned paper in e-readers.
Electronic paper is a fantastic piece of engineering. It's basically using physics to mimic subtractive color, but with electronics. Most e-ink systems use tiny capsules filled with charged particles in a fluid.
Usually black and white particles.
Right, charged white titanium dioxide particles and charged black particles. And below them you have electrodes. It's a tiny digital game of push and pull.
You apply a charge, and you can pull either the white or the black particles to the top surface.
Exactly, changing the color of that little pixel from white to black. And since it just uses reflected ambient light, it's very easy on the eyes. To get color, they just place a grid of tiny red, green, and blue filters over those black and white pixels. For our last section, let's go to the cutting edge, looking at color at the extremes. And first, we have to acknowledge a fundamental physical limit, the diffraction limit.
Okay, what's that?
It means that optical instruments, like a microscope, generally can't resolve details that are smaller than the wavelength of the light you're using.
Wait, so the light itself limits how clearly you can see. That feels so counterintuitive.
It is, but it's a hard limit of wave physics. And yet, scientists have found ways around it. We're talking about superlenses and metamaterials.
Sounds like science fiction.
It's profoundly weird physics. These superlenses use engineered materials, metamaterials, that have a negative refractive index. Now, normally, the fine details of an object are carried in what we call evanescent waves.
Evanescent waves.
They are waves that don't travel far. They hover right near the surface of an object and skate away incredibly quickly. A normal lens misses them completely, but metamaterials are engineered to capture and amplify those evanescent waves,
letting you see detail that should be impossible to see.
allowing you to resolve detail finer than the wavelength of light itself. It's seeing beyond the fundamental limit.
Let's talk about another one, quantum dots. This tech is already in high-end TVs.
Quantum dots, or QDs, are tiny semiconductor nanoparticles, and they are one of the clearest examples you'll ever find of the link between size and color. Here's the aha moment. The color a quantum dot emits depends precisely on how big it is.
So it's not the material, it's the size of the particle of that material.
Exactly. It's a quantum confinement effect. The smaller the dot, the more tightly the electrons are squeezed, which increases the energy gap between their levels, the effective band gap. A bigger energy gap means a higher energy photon is emitted.
Higher energy means shorter wavelengths, so more blue.
A blue shift, yes. So you could have a dot that's 5 nanometers across and it glows red. You shrink that same material down to 3 nanometers and now it glows blue.
You're tuning the color of light with a nanoscale micrometer.
That's a perfect way to put it. And it allows for incredibly pure, saturated colors. They're now replacing older phosphors in white LEDs because you can just coat a blue LED with different size quantum dots to generate the precise red and green you need for a brilliant, high-quality white light.
So to bring this all together,
Mm-hmm.
we started with this idea that light has no color. And we've seen that our whole experience of color is dictated by the scale of the interaction.
It really is.
Whether it's light traveling through miles of atmosphere, or interfering across a few nanometers in a soap bubble, or manipulating electrons inside a single quantum dot.
It connects every physical scale. And let me leave you with one last thought that brings us right back to history. We've been talking about cutting-edge nanoscale engineering. But consider the Lycurgus cup. It's a Roman artifact from the 4th century.
That's the cup from the sources. The one that looks ruby red when light shines through it, but it looks green when light reflects off it.
That dramatic color shift is because of nanoparticles of gold and silver alloy embedded in the glass. They exhibit something called scattering, which is a very sophisticated type of structural color.
So they were doing nanoengineering back in the Roman Empire.
In a way, yes. We're talking about gold particles smaller than the wavelength of light itself, which scatter light differently based on its polarization. That's why the color flips between transmitted and reflected light.
That's incredible. These principles that we're just now mastering with metamaterials were being used somehow by craftsmen almost 2,000 years ago.
It really suggests that there's profound optical science, sometimes hidden in plain sight, just waiting for our modern physics to catch up and explain it.
It makes you want to look closer at the world around you, knowing that every single color, from the sky to a beetle's wing, holds its own hidden lesson in physics.